Welcome back to the fifth and likely final part of my series on ultraviolet, the ultraviolet catastrophe. So today we're going to be looking at Planck's resolution to this problem, which of course is very important in physics in general at the turn of the century of the 1800s. There was an explicit assumption made that the energy function of the system is equal to nh nu, written here, where n is the number of photons or wave packets emitted from the black body, and u is the frequency of the radiation that's emitted. So obviously this is a huge jump, because if we recall from a previous video, we had what we would have assumed a continuous energy function. So we would have assumed that this system that we've talked about, standing waves in a box, would have a continuous energy function for any real particles inside. That would be what classical physics tells us. Of course, we're going to show this is an incorrect assumption. And in fact, this method that we followed here, where we went from the energy function to the average energy, we're actually just going to do that exact same step. We're going to do a sort of repeat of that step, but with this energy function. So this is a fascinating result in physics, and many attribute the birth of quantum physics to this very important theoretical result, along with other things like the photoelectric effect. Okay, so the first thing we're going to need is the probability distribution of the system. Now recall that, so it's 1 over z e to the negative epsilon over kt. Recall that our black body is still in thermodynamic equilibrium, right? So this body is in space. There's probably some particles or something inside, along with the standing wave setup. But this thing is in thermodynamic equilibrium. So this distribution of energy states is still valid. So it's incredible that this equation still holds. So we take this and we work it out in the discrete case for the first time. So this is going to be e to the negative epsilon over kt. And then to normalize this, we sum over all states of the system, e to the negative epsilon over kt. And to get the average energy is going to be the sum over all states of the probability and the energy function. And we've discussed this before, and why the rationale behind this. But this is really fascinating. So the states of the system have been redefined, which is an incredible thing when you think about it. So when we plug in the numbers here, or the equations here, we get nh mu nu over kt times nh nu all over the sum of e to the negative nh nu over kt. All right, so what is our summation over? Well, our new energy function is defined. All of the different configurations are defined by this number of photons. So it's discrete in nature now. This is an incredible sort of jump. So we go from n equals 0 to infinity. These are all the valid states, numbers of photons in the system. Sorry, those infinity signs are pretty bad. Let's do that again. But you can see that this is, we're only doing a slight tweak on one step. Okay, so we're going to need a mathematical tool here to help us. We're going to say let x equal e to the negative h nu over kt. Now I didn't come up with this, but this is there are a lot of mathematical tricks, I'll call them, in this derivation that are extraordinarily clever, and they let us get a result here that we can understand. Okay, so the new summation running from n equals 0 to infinity is equal to x to the n. If you look carefully, you'll notice that. And let me actually just shift this over, give myself some more space. X to the n, and I'm going to say n here, and I'm going to take the h nu outside. Okay, and then on the bottom, it's just n 0 to infinity on x to the n. So we have a couple of pretty simple infinite series here. So let's write them out. For x equals 0, well, this term goes away on top because n equals 0. N equals 1, we get x plus, I guess it'll be n equals 1, 2x squared plus 3x cubed, and so on. And then on bottom, we get 1 plus x squared plus x cubed. Some of these sums might actually be looking familiar to you already. We're actually going to take out an x on top. So that's the first thing we're going to do. We're going to take out an x. So we go x h nu times 1 plus 2x squared, 1 plus 2x plus 3x squared. I'm going to write out one more term, plus 4x cubed, and so on. And then the bottom is the same, 1 plus x squared plus x cubed, and so on. So I'm going to quickly show what these series are. Let's deal with the bottom one first because it's easiest. So we're going to say s is equal to 1 plus x squared plus x cubed, and so on. Pretty easy to see that this is 1 plus s times x, actually. Oh, I missed a term down here. Sorry, let me back up a step. The bottom summation, just to make sure I'm not doing things wrong, x0, x to the 1 plus x squared plus x cubed, and so on. Now if I do this correctly, this result will be right. Okay, so now you can see that this summation is equal. All right, so bring the s to the other side, and we will get 1 minus x equals 1. S equals 1 over 1 minus x. So many of you are probably familiar with that one. The other one is a bit trickier. The other one, we're going to say s equals 1 plus 2x squared plus 3x, 2x plus 3x squared plus 4x cubed, and so on. And we're going to do a trick that many of you may have seen in like high school sort of math, where you lay out all of the terms in columns according to their exponents. So we're going to first of all, we know we have 1, and then we're going to add a 2x times s, okay, and then we're going to subtract an s x squared s. So I'm not going to show you how you can get this result, but we'll just quickly do the math and see what happens. So we get 2x plus 4x squared. Is that right? Yeah. Plus 6x cubed. Trying to line up my my exponents here. And then minus x squared s, which is going to be minus x squared plus 2x to the 3, and so on. All right, and just bear in mind that this is actually subtraction down here, that one. So what do we get in the whole thing? We'll get, ooh, that line wasn't very straight. Let's do that again. We get 1 plus 2x plus 4 minus 1 is 3x squared, plus 6 minus 2 is 4x cubed. So we can see we got the same thing back. So s is going to be equal to 1 plus 2xs minus x squared s. All right, so there's actually a perfect square hidden in here. So bring all the s's to one side, plus x squared s equals 1. And you will see it now. 1 minus 2x plus x squared equals 1. And of course that can be factored. And we get s equals 1 over 1 minus x squared. Okay, so we have, I'm going to sort of group some things together now that we have all of our, like I said, all of the mathematical tricks have been done. So let's grab this one because we know that's an important definition we used to make this happen. And I'm going to grab this thing, which was the energy we're trying to get in the first place. Actually, this one. Just bear with me a moment. All right. So this was what we were trying to show. And we know that the average energy here, this is average energy, is going to equal x h nu times all this stuff. And I'm going to do yet another mathematical trick. This is going to be 1 over 1 minus x squared on top. And then, sure, let's leave the x there for now. I'll show you in a second how that works out. H nu. And then 1 over 1 minus x on the bottom. Of course, this just leaves us with x h nu over 1 minus x. We're going to divide the x out on top and bottom. So we're going to divide by x, divide by x, and we get h nu over x to the negative 1 minus 1. Okay, we should be, some of you who are familiar with the result will realize that this equation is of enormous importance. So remember that x was equal to e to the negative hv over kt. Did I do that right? You might have to do a footnote or something. Yeah, I did. A negative. Okay, so that's correct. So x to the negative 1, the average energy is h nu over e to the hv, or h nu over kt, minus 1. Okay, so this should look really familiar to a lot of you as that factor in Planck's law. So what I'm going to say for the rest of the physics is go back to the last video, and what you will find is that the rest of these factors are still accurate. Okay, it's really cool, but maybe I'll do another video discussing that. But the rest of the physics involving counting the modes and calculating the power output, all of that physics is correct. Okay, so this was the let's call this the classical version, and then there's a quantum version, where b nu is going to equal, so all of those other factors are still valid. So you have 2 pi nu squared over c squared times this average energy. And we just re-derived that. Average energy. So let's just write it in. Let's be complete here. It's h nu over e to the h nu over kt minus 1. All right, so this is a fantastic result in physics. What we find, and I'm going to do a very crude plot of this, but if you plot this spectral radiance, what you get is something, first of all, as a function of frequency, spectral radiance. You get something, oh, I'm going to butcher this, but it's sort of like a curve like this. No, let's try that again. I can do better. It's something like this. Okay, and remember, if you recall the original result like diverged rapidly. Okay, so this was the original. And obviously the area under our new curve, I'll do in blue, the area under the curve is finite. That is an enormously successful result in physics. I said this was going to be the last video, but I'm running out of time here. I wanted to talk about how, first of all, this derivation is, in my opinion, it's an incredible problem because it involves so many different aspects of physics. When you look at the fact that you had to use the probability distribution for thermodynamic equilibrium, you used the wave equation. There's a lot of really great theoretical physics in here. And I think the question that I would like to ask, and I would like to pose to anybody watching this, is does this imply that the model that we started out with, does it imply that this model is not representative of actual black bodies? You know, does it imply that, okay, maybe the sun doesn't actually fit this model? And I might do a quick follow-up video on that and some of my thoughts on it. But obviously we can see that using this, let me just find it once again, using this continuous energy function here is wrong. You cannot use this continuous energy function to derive the power output from this so-called black body. But when you make this energy function discrete, the answer is, it's incredible that it comes out with the correct curve. And of course the constants are obtained experimentally, but this curve in its form is absolutely correct for radiation that's emitted from a black body at different frequencies. Okay, guys, so that's it for my my derivation on this series. I hope you guys all enjoyed it. Please let me know what you think in the comments below, and like and subscribe it if you care to.